Dick told me he doesn't have an hour necessary, but I wanted to allow some time for discussion going along the way that would be potentially helpful in our understanding of this important message.
Thanks, Ken, I guess. When he asked me to come and do this, I didn't tell him I thought he was crazy. But I thought we'd give it a try. And rather than me coming up and saying this is the porphyry model from a geologic perspective, and then he coming up and do the geophysics, what we thought we'd do is flip the switch a little bit, and we would say, here's some of the geophysical responses that have been published and have been publicly available over porphyry systems, and these are some of the geological processes that can explain that geophysical response. We're going to flip the presentation just a little bit. Hopefully, it'll work. Okay, so just some bit of background to get us going. You know, porphyries are big, we all know that, and they actually produce much of the world's supply of copper and a lot of other important metals as well. We know that. They produce a lot of the gold, along with the epithermal system. But we also know that as the search goes undercover, geophysics is going to play an ever-increasing role in the whole discovery process. I like to use the word discovery rather than exploration, because most accountants think exploration is spending money. And whereas discovering is you're finding resources to keep the company alive. I think it's a very, very important distinction that we should start paying attention to. Anyways, so we know porphyries are associated with convergent plate margins. These are the old ones, the modern ones, and they are formed throughout geologic time. You get a question of preservation. So most of the porphyries that are actually produced metal now are from the younger systems, the latest Cretaceous down to Pliocene ones, but actually you have porphyry coppers that are known back into the Proterozoic. So they can be found around the world and always in a convergent plate margin. Okay? So we started this. So how do we use geophysics, or what can geophysics tell us about porphyry systems? And we can look at the continent scale, but that's probably not going to help us very much, although it will tell us where the major collisional origins are located, like the Appalachians in North America here, and of course the Cordillera that runs all the way up the western side of North America. So, but we can start at a much more regional scale. This is the which one? It is a reduced to pole mag map of Arizona with all the porphyry systems in here. We know they form an arc parallel system along in here with a couple of fingers that reflect a lot of younger deformation in different age camps. Okay, so we know that they form in these belts and that the geophysics can help us. When I first started working in Arizona, largely in this Never Land down here, I kept hearing about everything lined up along these great big lineaments, okay? And these sort of oblique lineaments that you see in Arizona are important for porphyry copper localization, and in fact what they represent are Paleoproterozoic terrain boundaries. So they're old crustal features that are localizing younger activity. So, I won't go through the details of this, but we have to look at porphyry copper deposits as crustal-scale phenomena. They start in the mantle, the process starts in the mantle, and goes all the way to the upper crust. So there's two elements that are really important. Perhaps the most important one is this great big upper crustal batholith. Okay, these are 10 to 15 kilometers across and a few kilometers thick. They're mushroom shaped, we know that. And these are the source of all the porphyry copper deposits. So the magma comes out the top along with the hydrothermal fluid and precipitates all the copper in the appropriate place under the appropriate tectonics, proper fluid chemistry, proper magma chemistry. Okay, so that's enough on that. So from a geophysical perspective, what defines a porphyry copper deposit? Okay, so they're always associated with an oxidized and hydrous magma. You have to have water in the magma system, in the magmatic system, in order to transport metal. If you don't have water, you're not going to get copper out of it. The magma associated with the porphyry system, there's nothing special about it. It has the average amount of copper. It's not enriched in copper, but it has a high amount of gold, and it's also oxidized, and I'll show you that in a minute. Okay? You also find them associated with major faults. The faults need not be active at the time. In fact, most of them are not. They are quite commonly an older feature that the magma has utilized to intrude into the upper crust. The porphyries themselves sits over the apical part of the intrusion. The apical part is just little pimples, little picachos on the top of the magma chamber. And those commonly form during the magmatic convection cycle. And it basically you have erosion of the roof. We know that the porphyries are large, and they have a low hypogene grade, generally less than 1%. Unless you have many superposed systems, you can get up to a couple % copper. But from a geophysical perspective, they actually form huge hydrothermal alteration systems that can be 10 kilometers across in the map view, and they can be 5-6 kilometers vertical. So each of those different alteration assemblies will give you a different geophysical signature. And then the last one is, depending upon the geologic history, the different depth of exhumation, that is erosion, of the system will give you a different geophysical response. And it's understanding that the influence of the geology, the intrusions, and the hydrothermal alteration is going to influence what the geophysical response should be. Okay? We good? Okay, so this is Ken's slide. Okay, what can geophysics provide? It's the magnetics, using that to map the structure, the rock types, and the hydrothermal alteration in a way. The resistivity maps the structure, the rock types, and the alteration, and veins. Chargeability, rock types, mineralization. Density, same, mapping the structure and the rock types. And radiometrics, mapping the lithology and alteration. And he's got a picture of the old, this is chargeability, right, Ken?
Yep.
Yeah. Oklahoma. Okay. And it's about 3,200 meters. And I had the privilege of working there in the midst a few years ago, just as they were opening up, and that ridge are these two. Okay? So they got a geophysical response here, but not much of the one under here, because these are thick post-mineral cover sequences that mask the geophysical survey. The porphyry now extends all the way across and is being mined on the other side of the valley. So it's become a true supergiant deposit. And here's just the pit in just a few years ago. There's that post-mineral cover, which is masking some of the geophysical response. It's an oligocene welded tuff. Of course, it's got the classic standard hematitic leach cap of a paleo chalcocite blanket, the geracitic leaching of a pyritic halo. This supergene calc blanket was down here, and now they're mining all the hypogene copper down at the end depth. Okay. Glad you made it, Brandon.
Thank you.
Okay, so what we'll do is work through those 6 topics. And we'll look at some of the geophysical response, and then we'll go back and say what it might tell us in terms of a geological process. Okay. So we'll look at the oxidized and hydrous magma. We know, and this is just the regional mag map from the Lachlan Fold Belt. These are Ordovician porphyry copper deposits in New South Wales and Australia. This is from John Holliday. And you can see all these very, very strong magnetic horizons. And within them is the Cadia cluster, Copper Hill, North Parks here, Cowell over here, the Marsden deposit. Cadia and North Parks and Cowell are the only ones that have been put into production, to my knowledge. but they're clearly associated with high magnetic rocks. Most of those magnetic rocks are basalt, so they're going to be high magnetic by definition. Okay? So, but nevertheless, the porphyry magmas are always oxidized. They always carry magnetite, and they carry titanite. And they also have high water. And why is oxidation important? So you have to put your geochemistry hat on here, guys. If I have to look at, whenever I used to sit in Doug Oldenburg's office, the first thing he'd put on is a differential equation. You know, and I barely made it out of calculus in 1974, much less 2006. So you have to look at a geochemistry. So why is that the average solubility or saturation of reduced sulfur in a magma is a few hundred ppm? Okay, you can't generate enough sulfur out of a magma that is reduced, has reduced sulfur to form a porphyry copper deposit. Because if you think about it, if your pyrite to chalcopyrite ratio is 1:1, which is pretty low, so there's 2 sulfurs in pyrite, and there's 2 sulfurs to 1 copper in chalcopyrite. So you got a 4:1 ratio. So if you want a million pounds of copper, you have to have 4 million pounds of sulfur. So you can't do that without an oxidized magma, because in an oxidized magma, the sulfur is in the oxidized form, which is +4 +6 valence, and therefore it remains in the magma as a sulfate. And you can have thousands of ppm of sulfur in the magma then. Then there's another step which follows, is that you have to then reduce that oxidized sulfur, but we'll get to that down the road. So what this just is a diagram that plots temperature. I've already lost one. And the fugacity of oxygen, and just the ratios of this SO2 to H2S. And these are just fields for oxidized granite. There's Pinatubo, which erupted a porphyry system, Volcani, which has advanced argillic alteration system in Peru, and Tampacan in the Philippines. They all have high sulfur dioxide to H2S ratios. Okay? That's really important. So mag is good, but it has to be oxidized too. Okay. For the next one, we hear about porphyries are always along big faults. And as a structural geologist, it drives me nuts that people have to then make that fault active. In fact, most of them, the evidence for that is pretty minor and minimal at best. And it can be along any number of faults, and the faults can be pre and post. And recognizing that is pretty important. So here's 2 maps from a recent Geoscience BC sponsored survey in central British Columbia. This is somewhere up in here. So here's a couple of systems. Gibraltar is a late Triassic system. Hapali is a late Triassic, early Jurassic, and they're in this sea of moose pasture, basically, muskeg, till, and whatnot. And so they flew the survey. This is the known geology, and this is the geophysical survey. And you start to pick up these great big linears in the magnetics, which are the faults, and you pick up the great big batholith, like the Hogan batholith up in here, which the porphyry systems are associated with. Okay. But on a more local scale, which one is this? This is La Escondida. This is the geologic map of La Escondida. Okay. The Falla Oeste system, the Domeco fault system runs through here, and here's the Domeco fault system. And the porphyries are basically in central Chile. You just map along the head frames of, well, in open pits. And it's along the Falla Oeste. Now, the Falla Oeste has a history that goes back into the breakup of Gondwana and the opening of the Atlantic Ocean. And there are these great big rift basins, and that's the inner margin between thicker continental crust in Gondwana and the rift basin on the west. And you can map that from Tierra del Fuego all the way up through Colombia. And that break controls a lot of the porphyry systems. Why? We can talk about that later. Okay. So that's a young fault. Bingham is an older one. Here is reduced to pole magnetics in Bingham in Utah. It's a giant system. Here's the geology. Park City is here, Park City is here, Bingham is over here. And you can see that a cluster of porphyry stalks coming off a larger batholith at depth are strung out along that contact. And that contact's a Paleoproterozoic suture zone between Archean craton and an early Proterozoic thing. It was favorably oriented to be dilatant, and it allowed the magma, the oxidized and hydrous magma, to actually come up and form the porphyry systems. Okay? So in the case of central Chile, it's a relatively young feature. It's actually have also post-mineral movement as well. And in Bingham, it's a very old feature. Okay? One is arc normal, the other one is almost arc parallel. So it doesn't matter as long as they are oriented favorably for magma to arise. And this is just puts Erzberg and Grasberg in along in Papua New Guinea along the arc parallel, fold and thrust belt. And these are cross-arc features that actually are inherited from the downgoing, the older rift basin and actually you can see them in the downgoing slab in the Australian crust. Okay, so let's skip on to the Pluton itself. Okay, in some of the geophysical images that Ken has provided, actually, some of what gets mapped is really that plutonic stock. And my favorite here is, of course, the Pluton in North Parks, again in the Lachlan. You can see here's the mag belt, and these are these deformed marine volcanics, largely basaltic andesites. And you've got this mag high sitting in here that actually you can see it's deforming the pre-existing geology. And these black dots are the North Parks porphyry clusters right in here. So you can see that in mag. You can see that at Highland Valley. There's is this mag, Ken?
Gravity?
Yeah, gravity, and this is magnetics, right?
Yeah, it's the Geoscience PC did.
Yeah. And you can see the cluster of porphyries associated really with the thicker part of that composite Pluton. This has got out of order. So this is the gravity signature at North Parks again. You can see the edge of the gravity. You can see the deflection in the stratigraphy and the E26, 31, 27. There's a whole bunch of these things. These are little pencil porphyry type things. And they come off the top of this monzonitic Pluton. So just to show you, this is what it works. I'm going to show you it. This is an inverted ground magnetic survey of a small porphyry cluster in southern Serbia, the Tulare district. And you can see the drill holes in here. There are 3 porphyry systems. 1, 2, 3. This is the one that's economic. Well, it was drilled extensively. It's not economic, but you can see it comes off a larger magnetic body that sits at depth. So this is the oven, and this is just leakage more or less. If you really want to get down and be brutal about it, this is what we want to find. But without this, none of that would happen. So this is how it really forms. Okay, you get an upper crustal chamber. It's convecting. As it convects, it starts eroding the roof because you're taking a hotter material up, you're scouring the roof. It will create a little cupola, an apical part. Commonly, if there's a weak point, like a fault, that's a much weaker point, and that will start to erode. And so you get this area that's like the lid on a pot. You start to collect the moisture, the vapor that is the supercritical fluid that's exhaled out of the porphyry in here. It cracks the roof, and up it goes. The magma follows, and you ultimately get a whole series of intrusions with a whole series of different pulses of hydrothermal fluid. Okay? So it's not a one-pass deal. And off we go. So, coming back to that mapping of the Pluton, Ken gave me this photo of the empty conductivity at Bingham. You got this great big conductivity high, 2 of them here. When you put them against the geologic map, this great big body is more or less this great big body here. It's actually the precursor stock. You're mapping the stock in this case and not so much the ore. But right in here, where the deposit is located, you've got this little wiggle in the conductivity gradients, and that might be essentially where the deposit is. Who knows? I've never understood conductivity or magnetics or density or anything else for that matter. When I went to undergraduate, there was no geophysics taught. Well, we had no geophysicists at the university. So anyways, so if we look at another example, this is from Cobre, Panama. I guess it's first quantums now. And these conductivity highs at shallow depth more or less correspond with the known ore bodies. At greater depth, of course, there's not as great a horizon. When you actually look at the geology, Cobre, Panama has been completely torn apart by younger deformation. And this is a master's thesis that Mark set. He reconstructed one of those. So this is the starting point. And when you pull those faults all back together, using a various set of criteria, you end up with a nice porphyry ore body. So what was being mapped, and it started here, is basically these various bits and pieces of a dismembered porphyry copper deposit. That's not to denigrate the fact that the conductivity mapped great, but it's also really mapping the pieces of the porphyry. And then from a perspective of reconstructing a district, it is actually a very, very useful tool. Okay. So let's get to hydrothermal alteration, which you guys probably know enough about, so I'll quickly get over that. So here's something that Oshki put together from Baja Alumbrera with the various magnetic geophysical signatures, resistivity, magnetics, the radiometrics, potassium, and topography. So we've all seen pictures of this. It's an actually beautiful, beautiful little valley in here with the core of the high quartz vein density sticking out. So the geology is over there, but I thought we'd look at the cross-section, which more or less goes like that. It's much easier, because what we're really mapping here, here's the topography. That's the topography, because you're mapping a sericitic margin and a potassic core. So that's what you're looking at. Here is the high quartz vein density. Here is the magnetic core, and that's the sericitic and potassic alteration. So if you look at it in terms of grade, oops, I went one too far. Here's your 1% copper, right smack under the high resistivity because it's the highest quartz vein density. That's quartz veins over 50% by volume of the rock. So it's going to give you a huge resistivity high. And in flanking it, the copper grades are lower, and you have the sericitic overprint, and you'll get the potassic halo out. So another one from Badahija pretty much tells you the same. Okay, and you've got a high mag in the core. Okay, where's the magnetics? Right there. Okay. But when you look at the geology is telling you that all that stuff sits over the biotite, magnetite, chalcopyrite, bornite core with a surrounding overprint of the sericitic alteration. And we'll look at that in a minute. Okay? But as you know, Not all porphyry systems have a magnetic signature to them. Some of them are magnetic holes surrounded by rock. So this is red Chris up in northern British Columbia. It's associated with this monzonitic stock and placed into mafic volcanics up in here and mafic-rich sandstones and shales and whatnot of much older. It is bordered by this fault system with post-mineral rocks on the southeast. But you can see the east zone, main zone, and the gully and far west zone have somewhat different magnetic signatures. So what that is telling you, what is it, is really it's the hydrothermal alteration that is driving that, plus the host rock differences, because you got a monzonitic stock intruded into mafic-rich rocks. So by nature, they have a very different magnetic response. So you can correct me if I'm really out to lunch here, but anyways, here's the stock, and you can see the change in the rock character as you go across. This is just a piece of drill core. Okay? But it actually is, if you turn it onto the side, would be the porphyry copper deposit. This would give you magnetics, but all the magnetics here are being wiped out by the hydrolytic alteration assemblages. So this gives you your mag low. So that's this diagram that Dixilito uses and everybody uses, okay? The potassic core, the acidic, and up to the advanced argillic. And Brandon, I think you were here when we took that picture. But this is a picture that basically shows you that same relationship. High magnetite being wiped out by the acidic alteration and giving you basically virtually no magnetic response whatsoever. I think I'll just go ahead and skip that. So the point that I want to leave is all porphyries are not made the same. There's a tremendous variability amongst them. And that variability is a function of, the composition of the intrusion that's driving the porphyry system. It's a function of the sulfate to reduced sulfur ratio that comes out of the fluid. That is the level of oxidation in the magma. And also on top of that is the depth of formation. They don't all form at the same paleo depth. They can form from about 2 kilometers. Some people will go as shallow as 1. 1 kilometer will give you maybe down to the deepest ones, which are there at Butte, which might be forming as deep as 8 kilometers. So that reaction, this reaction here, which takes your oxidized sulfur, reduces it, gives you a bit of acid. That's the critical reaction that gives you the amount of reduced sulfur to combine with copper and iron to precipitate your boronite, chalcopyrite, and pyrite. Okay, that's going to give you the grade. Okay. That reaction has a temperature and a pressure function to it. That is a depth. So it happens at much higher temperature for porphyries placed at greater depth, and much lower temperature at porphyries placed at shallow depth. So if we take that one step a little farther, most of your copper gold systems, when they actually go look at them, are relatively shallowly emplaced. So they have a lot more magnetite in it because that dissociation reaction happens at a lower temperature. Your copper moly systems tend to form at a slightly greater depth, and they generate a lot more acid, and you get a lot more acidic, and you tend to lose a lot of your magnetic character. Okay. So there is this crustal dip. So let's build one. Okay, just to give you. So this comes from Yerington, Nevada. It's a Jurassic system. It's not the world's biggest, but it's probably one of the world's best understood from terms of its geologic evolution. And that's simply a function that the tertiary extensional deformation in the western U.S. has taken huge blocks of the Jurassic Arc and turned them on its side. So now, when you look at a map, you're looking at a cross-section. And if you really ever want to know what one looks like from underneath to the top to the lithocap, it's the only place you can do it. Okay? Most of what you see are horizontal slices at different levels. But this place you can actually walk the entire system. They're not big, and you don't actually see the porphyries outcropping except in a few places. But anyways, so here's your batholith, a composite batholith. This is the host rocks, the volcanics, the country rock over here, and this is the youngest of the Plutons and volumetrically the smallest one. Actually generated 4 porphyry copper deposits. And if you aggregated them all together, it would be a supergiant, where you take all that contain copper. The grades are 0.4. They're not great. But if you stuck it all in one place, it would be pretty good. So coming off the roof, in the cupolas, you've got the high temperature biotite alteration, with the potassic alteration. And as it goes up, temperature cools, you start to dissociate, you start to generate acid, you form the sericitic, and as you get up to the lithocap, it gets very, very acid because you lost all the buffering capacity of the rock, and you start to generate the quartz replacement and the advanced argillic alteration assemblages. As the system gets chugging along, you've got this big heat source out here, and you start to drive geothermal circulation. This is the propylitic alteration. And if you're lucky or cursed, depending on your point of view, if you have a little bit of salt in the country rock, marine volcanics, evaporitic sequence, sedimentary sequence, at higher temperature and greater depth, you generate sodic calcic type alteration. And actually, as people drill deeper underneath El Salvador, they have it. And as people drill deeper, many of the BC porphyries have it, you start to get a sodic calcic alteration assemblage. And that's actually really bad for most porphyry copper deposit because that brine, which is what it is, that brine removes copper. Okay, it destroys grade. But anyways, so you get these big circulation systems. These are geothermal systems. They're driven by the heat of the magma. And in the case of Yarrington, because they had evaporites in the sequence, they generate a lot of salt. So you got these huge volumes of sodic calcic, and they grade upwards and they more or less merge into the bottom of what is called propylitic alteration. So propylitic alteration is more or less the ingredients, the cake ingredients are already there, and you just add water and CO2 from the groundwater. But sodic calcic, you're actually adding a salt, you're adding a brine. Yeah.
The scale here is impressive.
It is.
But the reason this isn't just imagination is because of this rotation. Do I understand correctly that this information down to 7 kilometers is now basically at ground surface, more or less?
You see these dots?
Right.
That's the known. Okay.
Oh, okay.
All right? These dots, so they know some of this, and they infer other bits of it from the geology.
But they have a good chunk down to 5 kilometers or so.
Yeah, they can go all the way down here, and actually, which is not shown on this diagram, they actually have the base of this Pluton. You can go actually see the base of the Pluton.
Do you know, at the one with the little crosses, is that contain magnetite? Is that
Oh yeah.
It's magnetic?
Yeah.
Okay.
And it's got great big orthoclase phenocryst, and it's got it's basically a Monza granite. It's almost a granite porphyry. I think it's got somewhere in the 68%. I can't remember exactly, but it's not a true granite, but it's not a granite-aura. Sort of that in between. So the sequence here is the first one is more mafic, and then it gets less mafic, and finally the youngest is the most felsic of them. Okay, so it's the lower granite porphyry, and all the dikes are emanating from that intrusion. You can actually get on the dikes and walk them until they disappear.
Okay.
And you know they're there, but you can't find a contact, you know. And it's really quite an impressive place. And you have to go with the right people.
Dick runs a field trip there.
No,
so-
but yeah, I'm saying John Dillis. You have to go with John Dillis, not me. Yeah, we do run a mapping course there every year. But then finally, what happens is the first aliquot comes out of the roof, but as the magma crystallizes, the magma, essentially the source, goes farther and farther and farther down. So to travel from 7 kilometers to the porphyry level here, it has a 4-kilometer vertical. The first comes out at 4 kilometers and doesn't go very far. So that fluid aliquot is hot. It's going to form your potassic alteration. This fluid aliquot coming from this down is cooled through water-rock and interactions. And when it hits here, it has a different chemistry. So the net effect is the lower temperature, more acidic alteration assemblages are progressively overprinted on the higher temperature. Okay? That's probably more you want to know. Anyways, so sometimes we know you get a lot of porphyries in the same place. Many of the porphyries in Chile, we know, are magic strikes more than once in the same place. And sometimes you actually are spatially separated where you can actually see them. And this is a map that Abdul Razik did for 2 of the 4 porphyries in the Western Porphyry cluster in Reykjavik. And their alteration halos begin to overlap. So they actually would produce a giant geophysical survey anomaly in a sense, this hydrolytic alteration. But the alteration mineralogy and hence the physical properties of the geophysical survey will be slightly different because the alteration history has been different. Okay? I'll just show you. Here's a long section of those 4 porphyries, H79, 15, 14, and 13. That just means which whole number it is. H doesn't stand for anybody. So they're very, very simple porphyries. Okay? But the 5 billion tons or 6 billion tons really is all within these. So if we look at the alteration, you can see something very different, slightly different. This has a lot more hydrolytic overprint on it, so whatever geophysical response is going to be different than this one, which has your potassic core, the magnetite, K-feldspar, biotite, and hydrite quartz, all the way to the surface. And it also has very different grade. Now, I don't know where that one went. Anyways, we had the grade, it was the grade on here. We've lost a slide, but anyways. So this one actually is the key for making this economic, because you have bornite, a very, very huge bornite core in this one, and it's missing over here. It's not as well developed or preserved. We don't know. Okay. So let's look at more in detail of one of these porphyry pits. This is the Yarrington open pit. It produced 160 million tons. I forget the grade, 0.5, 0.6. It has no moly, no gold, but it was pretty much a copper system. So this is the long axis of it. This has been tilted over 90 degrees. So you're seeing the cupola is down here. The dikes come up. The dikes all dip about 45 degrees. Oops. 45 degrees to your left. And the potassic alteration is here. It's a little bit brown. And then you go into the hydrolytic xerositic alteration up here. And that's the tertiary unconformity, that there's a minuscule amount of supergene enrichment. Okay? So when we run this mapping course here, we always give everybody the song and dance over what the geology, and then we ask them what's the pH of the pit. Anybody want to venture? Okay, think about it. See all this white rock? That's sodic calcic alteration, rich in feldspar. This is your potassic, and this is your pyrite-rich rock. Okay. We'll go back to that in a minute. It's pH 7 because of the feldspar. Anyways, so here's the geology that John Prophet put together. I haven't tried to orient them up. This piece would be in this part of the lake. That piece is down there, okay? So you have a whole series of very narrow dike-like bodies, and they have them QMP1, QMP2, QMP 1.5, and 2.5 because the mine geologists found it after they had already done a QMP 1 and a 2. And they actually, there's a compiled map that Marco Einaudi has, which I've never seen, but he's taken all the mine geologist maps and put it together. It would be phenomenal, and we've been all trying to get him to actually publish it. But the geologists were only allowed in there because the mining engineers were getting poor recovery because they weren't paying attention to the sulfide distribution. Anyways, so here's the mag. If you look at it, the mag goes with a late porphyry that still has a bit of its primary magnetite in it, particularly this body down in here. It's a QMP 2.5, I think is what it is. And the chargeability is here, and this thing is the core, and there's the acidic alteration. That would be all of this stuff over there. Is that right? Yeah, lows are blue and highs are the red. So this is Hunter Ware, put it out in 1979. I never knew it existed until Ken sent it to me. So, the porphyry system starts here in the fluid-saturated carapace, goes up through the copper-rich core, comes out the lithoket. Okay? So depending upon the level of exhumation, you're going to get a different geophysical response because the physical properties of the rocks will be different. So if we look at it from Badajoz, this is stuff that Steve Garwin did extracted from Newmont. Okay, paleosurface, you'll have high chargeability because you're up here in the Acidic. Radiometrics, because you have a lot of potassium. You've actually moved a lot of fixed iron. You've actually moved calcium and magnesium, so you've increased the potassium. You have a high magnetic core because you're starting to get the potassic alteration. You get a high chargeability because you're getting more sulfides. And you get down at the porphyry level, and you get what you'd expect. Okay? So I think this is the last slide. And this gentleman put together, here is the general geology with the distribution of your alteration assemblages. And depending upon the level of exhumation, you will get a very, very different geophysical response. And that's really the important point, is that all porphyry geophysical surveys are not going to tell you the same thing. And it's the question that properly has to be addressed to the geologists, and they should know this, is what could it be? What are my options? And again, here's Badajoz with a magnetic high in the middle, and here's Red Chris without the magnetic high, each of which are somewhat respectable porphyry copper deposits. So I think that's the end. So I hope I didn't brutalize geophysics too much.
Well, you did a good job.
I call myself a geophysical dummy, and that's probably the best I can call myself.
So the message I get is that geology is easy, the geophysics is the problematic one, right?
No, it's actually and you know
challenge.
this. It's getting the geophysicists and the geologists into the same room and talking. Is that right, Brandon?
Yeah. I got a few questions.
Go for it. You want a microphone?
Firstly, Dick, really appreciate you coming down and giving this introduction for us. First question, sort of going back to the start of your presentation, you talked about the sort of, it's a pretty known criteria about the presence of an oxidized source, magma, Pluton, right? And then sort of inherent or implied in that is that you'll form magnetite and you can pull enough sulfur out and make chalcopyrite, right? So, yeah, does that, and this might be my ignorance, but a lot of the time you'll see these big magnetic sources under the deposits. You showed Bingham, we see this regularly right all over the world. How would you explain, hopefully you're familiar, with the Globe Magma district, and there's a really big elongate mag lobe sitting under the entire district there, in that context of having the right oxidation state.
Yeah, well, let me take a crack at that one since I've never seen that. But my geophysics colleague have actually finally beaten into my thick skull that any geophysical survey is looking at physical property contrast.
Yep.
So are we looking in those cases where you, like in the case of North Parks, where you actually have a monzonite, which has a very different magnetic character embedded in a series of basalts.
Mm-hmm.
So are we looking really just at a physical property contrast rather than something else?
Fairly, well, it's a good question, a good reply. I'm fairly certain it's not a relative load, it's more of an absolute load. But I mean, I'll send you an image. I'll send you an image.
Yes, please do.
Second question then, sort of on that same scale, you sort of talked about the deposits kind of forming over the kind of epicenter, right? Like right in the middle of these things, the apex. You show North Parks. But then if you go forward ahead and you show Yarrington and you show the batholith, and actually, it's close to the margins where some of these cupolas started forming, right? And I have seen this before, that the margins of these larger...
Well, actually, I can dig it up on my computer, but they're actually, when they reconstruct that back together, they're smack in the middle. Yeah. Now, there are a couple dike swarms off on the side in the Yarrington, but the main one, the Yarrington and Mason, Bear, and MacArthur, they all are pretty much in the middle. And so much of that, I mean, it's a great question, is when you think back on magma, magma chamber dynamics, okay? Things crystallize from the margins in, so that's number one. And they don't stay molten for very long, so they have to be recharged, okay? So you have to get, new stuff comes in, okay? And that has to come into some vertical permeability fabric, like old fault system or whatnot, okay? And it comes in, tends to be more mafic, and it starts to drive, because you're sticking a Bunsen burner underneath something. It's like boiling water. It starts up over the heat source. So that then starts it up. And so I've always wondered, is like the big systems like the Faya Oeste, the one that Bingham is on and whatnot, is those things they have a vertical extension in the crust. And so where the porphyries are coming out is probably where the magma is coming in. And what it's starting to do is drive this geothermal circulation. Because as you take a piece of magma here that's fluid saturated, high, 4 or 5% water, and you take it from 10 kilometers to 5 kilometers, you reduce the litholytic load, and the fluid comes out. It's just adiabatic decompression. So I don't know if I've answered your question. I sort of went way over here.
I kind of think the location of this pre-existing deep-seated structure relative to where this source melt comes up is probably more important than that location.
It is very important, absolutely.
I mean, the Highland Valley is a good example. That valley is the best deposit at HEC is right in the guts of that.
Yeah, you're absolutely right. I mean, it's the magma's I always tell people, magma's a fluid. It's a very viscous one, but it's basically a fluid. If you got a hole in your roof, that's where the water's going to come in. So if you got a crack in the crust, that's actually an area of reduced, I won't give you the full structural geology thing, but it's lower pressure. The magma has a higher pressure, a lower density. It allows it to go upwards, yeah, absolutely. You're doing great. Keep going. Yeah, I got like 2 minutes to go. Keep on going.
Sorry for anyone else. Please interrupt me. John's going to interrupt me. This red crystal hydrogel contrast that you're showing is interesting, and you know, I would like a bit more commentary on the effect of hydrolytic, as you're calling it. Philic, whatever we want to.
Yeah, well, it's the same thing. It's just one's a chemical reaction and one is an alteration. So
generally, I kind of had an impression in my head they really killed off the grade, and you did suggest that for Samuku, but now you're saying a red crisp. Well, even though it's got a heap of hydrolytic alteration, it's pretty good deposit still. So I'm interested into why it's sort of still a good deposit, even though it's got this overprint.
why it's strong in some places and not in others? Is that what you're asking?
Yeah.
And that comes back, well, there's two reasons. One is exhumation. If you've already eroded through, then you're not going to see that philic overprint. The other one is more, if you're looking at this, you know, the whole thing, and you've not eroded, it depends on, and I won't bring out that phase diagram, but it's the reaction that goes from SO2 plus water gives you your reduced sulfur plus a little bit of acid. That reaction goes at lower temperature at shallow depth, and it goes at higher temperature at greater depths. Okay, and that's a function of the porphyry emplacement environment. Okay, so the boys that do bubble work, fluid inclusions, you know, they have argued that in the copper gold systems, the fluid inclusions are telling you that they're forming at a much shallower depth than the copper moly systems. So 2 kilometers or thereabouts and 4 kilometers or thereabouts. Okay, those are averages. Okay, so what that tells you is that at the copper mag systems is that hydrolytic alteration copper gold systems that still have a lot of magnetite. They may be much lower temperature. They have a lot more magnetite, so that you're getting magnetite is precipitating at high temperature. Okay, whereas in the copper moly systems, remind me, I'll come back to that one in a minute, forming a bit deeper, and so you're generating a lot more sulfur, a lot more reduced sulfur. And in many cases, I've always wondered if there wasn't at high temperatures a lot of magnetite in these copper moly systems, because it's forming at 500, 600 degrees, right as almost when it comes out of the magma. Reduced sulfur's coming in at 450, 400. Are you then sulfidizing the magnetite to produce pyrite? I've always wondered that, but I've never seen anybody actually talk about that.
That could explain some of these observations.
Yeah. So it comes down to the pyrite gets generated, the vast volume of sulfide gets generated with this dissociation reaction. Okay? And that has a depth function. It also has a control by the original fluid composition as well. And
my last question, comment is, you kind of step through these 6 different aspects and their effects on geophysical manifestations. What we probably didn't discuss, and I could argue is pretty important as well, is supergene effects and weathering oxidation, which, you know, let's look in the backyard here in the Laramide. It's another added layer of complication on top of these responses. I decided that I sort of almost exceeded my geophysical comfort, and so I was good up to his point.
Oh, Brendan, what the Globe Miami thing?
Yep.
Have you tried something like the Voxy MVI to see if potentially is there a remnants issue with this well?
Yeah, it's not remnant. But I know you guys have heard of it as well, Ken, so you know the answer.
Well, tell us.
We're non-denominational.
You agree with me because I've seen John's stuff from it, right?
Okay, sorry.
Thank you for it. This is great. This is fantastic. It's a great explanation. I want you to explain to me the difference between alkalic and calcalcalic porphyry systems, because that wasn't mentioned here. And what I see is when we fly calcalcalic systems, they have fantastic. We see fantastic alteration patterns. Whereas when we look at alkalic ones, you don't.
Yeah, you
And here's
do.
another.
Yeah, you do. Absolutely, you do.
I'll show you no oxygen.
Absolutely, you do. It's that no one actually ever looks at it. Oops, I went too far. I know if I try to log out, I'm going to screw it up. There we go. The difference between alkalic and calc-alkalic really drives from the magma. Now, red crust, the example I showed, gets lumped into the ones in Cadia Valley and North Parks, they get lumped into the calc-alkalic, but really when you look hard at them, they're transitional. They're more or less Shoshonet high K. And then the only really true alkalic is Galore Creek. I mean, it's one of the weirdest deposits in the world, but it has all the same alteration assemblages. What it's missing, and which nobody has ever looked at because it's up the hill, is that sericitic plume, which has all the geochemistry that you find above a copper moly system, and it has the alteration assemblage of sericite, chlorite, and carbonate. Okay? So that system doesn't generate as much acid as the copper moly systems. Now why, I have no idea. But that's what you see above Galore Creek if you went up the hill. And they're there.
Right, all I can say is for me as an airborne geophysicist, you see geophysical responses like resistivity, mapping resistivity. The alkalic ones is very, very subtle.
Yeah, it's definitely more subtle.
Alkalic is a lot more.
Well, they're bigger. Yeah. I mean, that's basically the upper left versus the lower right.
Okay.
I mean,
Here's my second question.
yeah.
Coburg, Panama, and I didn't know, I didn't know that those were, it makes a lot more sense for me.
Yeah.
Now that I see that, because it makes more sense to me how the ore body is shaped. But did you know, like, what makes those things conductive?
Well,
Because there's no secondary enrichment in them.
okay. I've never been there. Okay, so I'm going to take a stab in the dark.
I'm kind of like wondering, is it possible that you like you talked about the acidity of the water, of the groundwater. Is it possible that it's the acidity of the groundwater contained within these porphyries that makes them more conductive?
I don't know, but my bet is what you're looking at is the individual pieces of the stock that have high vein density and therefore still have high grade. So that's my bet of what you're actually mapping is a rock contrast. But the rock is not just an intrusion, but it also has all the hydrothermal alteration in veins.
I was just wondering, maybe because you're talking about pH of water, whatever,
Sure.
whether that was a contributing effect.
Yeah. No, I've never been there, and the people that have worked there said, well, good luck seeing a rock, because mostly what you see is saprolite, an outcrop.
What, Norm, you've done a fair bit of near-surface stuff, maybe in fairly acidic environments, and maybe other people in the room, but I mean, is there a rule of thumb, if you've got a pH of 3, do you have a resistivity of 50 ohm meters, or, I mean, I think we've, as a community, we've done enough work in those environments to have some feel for it. Is that, doesn't matter whether it's a porphyry or a garbage dump to me, if it's the acidity that's controlling it. And it's obviously aqueous, right? Yeah.
Right, the times that we've worked in an environment where we had some information about pharmaceutical ones, certainly those were very high.
Yeah.
Oops, can't get it to you, Norm.
Well,
And no one can hear you, I couldn't hear you up there.
okay.
either.
Well, I was just going to say, the few times that we've had the background information in the situation you're describing, it was very conductive, getting down less than 10 ohm meters actually. So on a larger scale, less volume, but I can't say we have enough background information, but that's the direction I would go. Yeah. very.
Well, take a guess, I did.
I think these rocks are so low porosity, these igneous rocks, that I don't think it's a water story, Ken. It's my personal opinion.
Or acidity.
Yeah, or acidity of the composition of that, any fluid in any pores. You know, they're sitting around 1% porosity.
It
Maybe like,
rains 5 meters of water there a year.
yeah, but the rocks are but if we were in a sedimentary situation, then we'd be driven by porosity.
Okay, I think we're
We're
done.
not.
Do we gotta move on,
I
Ken?
think it's
Yeah, we're good.
it's not. I don't know the answer, but it's a really good question.
Okay, well done, thank you.
Actually, I was gonna ask Jimena because if she recalled, but at the field trip, we went to Baghdad on Saturday, and they actually had hydrogeophysics doing some resistivity because they have issues there with acid mine drainage. They've had a lot of tailings, historical tailings, and a lot of the rock is decomposing because of this. And as a result, in the pit itself, there's a lot of failure that's occurring because of these structures with acidic waters coming through and basically physical weakness of the rock. But I was trying to think of the sections that the geo was showing as to whether it was particularly conductive. They had highs and lows, but I don't know if we saw a geological section to go with it, but there may be something they might be prepared to share just to try and I'll ask Mark about that, whether we may be able to get a hold of that. So